Sharing screen. Let me know if you can't see my slides. I appreciated it last week when somebody mentioned that I was talking, but all you could see was my face. This is where we left off last time. We were talking about the idea of building a project or building a program that was big enough that we had to split it between multiple implementation components. We learned about the idea of declaring things, either variables with external variable declarations or functions with prototypes that were defined in other components. And then we just learned about the idea of marking things as static. If you have a component that marks a variable as static or a function as static, then that is like an internal implementation detail to that component. Other components, even if they try to access those, they won't be able to. Sorry, I'm just changing the Zoom window over here. Even if they try to access those things, they won't be able to. The linker for things that are marked as static, it treats them kind of like private in Java. It makes it so that other components can't access them. This is one of our few things in C that lets us build projects with multiple components where each one can have things that don't necessarily collide with others. If we're compiling a program that is made of multiple components, that has multiple .c files, typically each of them with their own header file, then for large projects like that, we probably want to be able to separately compile and link them. That will let us, it'll let us manage a big project like that much more efficiently. We don't have to compile it all at once. We can compile, like if we go in and change just one source file, we only have to recompile that one source file. To do this, we need to be able to separately compile and link the parts of our program. So that's the next thing that we're going to see how to do. We talked about that, I think, since the first day of class. We just haven't been using the compiler like that. But let's say you have a program, same kind of thing we've been talking about. It's got two pieces, main.c and stuff.c, and you want to, and let's say main uses some things from the other component from stuff.c. Let's say we want to be able to compile both of those separately and then link them together. We can do that. We just need to tell the compiler what steps we want it to run. And in the past, probably until today, you could compile a program that had multiple source files and link them all together all at once. And a line like the one I've got up here at the top would do that. You can just list multiple source files on the GCC line, and this will compile and link them all together. But if this is the only way you knew how to do that, every time you wanted to recompile your program, you would have to recompile both of the source files. It could be a lot more efficient to compile them and link them separately. And that's what I'm showing at the bottom of this slide. If you put a -c option on the GCC line, that tells the compiler to just compile that program, just generate what we call an object file for that program, just generate a compiled version of the program or of whatever source code is in that file. If you compile the two programs the two source files separately, each of them will automatically generate a .o file. And then if you want to link the two of those together, you can run GCC and then list all of the object files that you want to link together, name the output file you want to make, and it will build an executable for that. I've got an example for this. Yeah, so here it is. I'm logged on to the remote Linux machines. I've got the same source files we've been talking about. If you look at stuff.c, you can see it defines a global variable x and a function f. If you look at main.c, you can see it tries to use that global variable x and it tries to call that function f. It includes the header file for stuff. And if we take a quick look at that, you can see it has an extern variable declaration for x and a prototype for f. So as long as main includes this, the compiler should at least know about these two definitions. If we compile them using the commands we just talked about, so gcc -wall -std equals c99, let's tell it to just do the compilation phase on main.c. And then if we take a quick look, you can see that generated a file, main.o, an object file for main. So that's all the stuff defined in main, compiled to machine code that is ready to run on this particular system. If we sneak in and do the same thing with stuff.c, and then take a look, you can see we got a stuff.o file over here, an object file compiled from that source file. And then the last step was to link the two of these together. And we said if you run GCC, and then you just list all the object files that you want to link together, main.o, stuff.o, and then since here is where we're creating the output file, we're creating the executable, here's where we pick its name. I'm going to call it just plain old main. And then if you take a look, we do have an executable main that just got created that is the result of linking those two object files together. If we ran this, it does what the main function, it does the code in the main function, which looks at the variable x and prints that out, and then calls the function f, and it prints out the result of what it was called with. So this is us separately compiling each of our source files into object files, and then using GCC to link them together. Even though all these programs are called via GCC, this is us separately invoking the compiler up here and then invoking the linker to link together the two objects. If on a bigger project that is split between multiple source files, we might start getting error messages from the compiler. And what I'm trying to say here is it is worth it to try to be able to tell the difference between compile time error messages and link time error messages. When you compile a program, if the compiler catches you trying to access a variable or call a function that it has never heard of before, it'll give you a compile time error. And this is the kind of thing that'll typically look like. If the compiler says implicit declaration of some function, that means that you're trying to call a function that it's never heard of before. That's usually because you're trying to call a function that it hasn't seen a prototype of before. If you're able to successfully compile your program, and then when you try to link it, you try to glue together the definitions of a function in one .o file with the uses of those functions in another .o file, if that has an error, you'll get a message that looks more like this. A link time error is going to look like undefined reference to some function f. Telling the difference between these or being able to recognize the difference will help you make sense of things going wrong within your program. Questions before we move on? So backing up a slide or two, here I'm just trying to tell the difference, or I'm trying to show an example of a difference between a compile time error and so something the compiler might complain about if you try and use a thing that it's never heard of before versus a link time error. There are some tools that can help you figure this out. One of them that we can try out is nm. Like a lot of Unix commands, it's got a really short name. This tool will let you see all of the symbols defined in a particular object file. And if we go look at the stuff we compiled earlier, so a few minutes ago, I had our terminal window. I compiled each of main.c and stuff.c, and each of those built an object file. And we can see the files for those, but if we wanted to look inside them, if we wanted to see the symbols that they define, that's what nm does. So if we run let me bring up stuff.c just to remind you of what's in it. It's got a global variable x and a function f. We compiled it already, and that generated this stuff.o file, an object file representing what's defined in that C file. And if we run nm on that object file, stuff.o, you can see it prints out for every symbol, for every identifier that's defined in that file, it prints out a line saying that it's defined there. So this first line you can read as saying there is a function named f. I should pick more expressive names for these so that this line looks a little more meaningful. But if we take, again, a quick look in this, it defines function named f and a variable named x. And if we run nm on it, it reports that there is a function named f that's defined inside that function, and there's a variable named x that's defined in that function. This printf is showing that we use a function called printf, but it's not defined. This u here means it has to be, the object file uses it, but it's not defined in that object file. So it's the linker's job to glue together this use of the function printf with a definition of it from somewhere else. That definition is going to be provided by the standard C library. Printf is a standard function, and the job of the linker is to glue together any uses of variables or functions with their definitions. We took a quick look at stuff.o. Let's take a look at main.o. You can see the same kind of thing here. In main.o, we call a function f, but it's not defined in main.o. The job of the linker is going to be to glue together that call with the definition here in stuff.o. Same thing for this variable x. We use a variable x here in main.o, but it's defined in stuff.o. So the job of the linker is to hook together uses of things in one object file with their definitions, either in another object file or a library like the C standard library. And this should match the same thing we were just looking at. I did it in the opposite order here, but this is just showing what NM reports when we look at the symbols defined and used in main versus the ones defined and used in this other object file we made. Questions before we move on? So what I think I'm trying to explain is the different phases of compiling and linking a program, and I'm trying to use a tool called NM to show you a little bit of what the linker does when it builds an executable for a program. If you let me back up a couple of slides, I said if you had a big project, it would be a lot more efficient to try to compile each of the source files separately and then link them all together once they had all been compiled. The reason that would be more efficient is if you started making changes in that program, you would only have to compile the files that changed and then link them all together. But if you had a project that had dozens or hundreds of files in it, this could require a lot of typing. So it is handy that we have tools that do build automation for us. And one of the oldest and simplest tools for doing this is a command called make. Make is a program where you can describe how to build a program. You can describe what all the source files are. You can describe when they need to get rebuilt, what they depend on, and make will do the job of automating rebuilding that project. So like I tried to say a moment ago, a lot of what you end up doing in automating the build process for a larger project is describing dependencies in that project, saying whenever this file changes, here's what you need to rebuild. So if we're writing a make file, a lot of what we're going to be doing is describing those dependencies. Most of what's in a make file is a list of what are normally called rules for saying what I was just talking about. When this file changes, here's the thing you need to rebuild, and here's how to rebuild it. That list of rules we will write down in what we normally call a make file, and then the command make is a program that knows how to read and interpret that make file to rebuild our project selectively, to just rebuild the parts that need to be rebuilt. It's the same set of code we were just talking about, and this tries to show the dependencies between the parts of the project and tries to show what parts need to get rebuilt if a particular file changes. So we've got 3 source files. We've got source stuff.c, main.c, and there's a header file, stuff.h, that advertises what is defined in stuff.c. If just this one.c file changes, stuff.c changes, what do we have to rebuild? Well, main didn't change, so we don't need to rebuild its object file, but stuff.c did change. We have to rebuild its object file, and then we have to relink the 2 object files together into an executable. These are the kinds of things that are captured in a make file. If the header file for stuff.h changes, and main includes stuff.h and stuff.c includes stuff.h. If this header file changes, then we have to rebuild both of the object files and relink both of them together. Describing a make file is involves describing how these different components of your project depend on each other. In a makefile, like I said a moment ago, a makefile is a system, is usually a sequence of rules that describe what has to get rebuilt and when it has to get rebuilt, based on what it depends on. And these rules come in the form like I'm trying to show down here at the bottom of my slide. Every rule starts with a target. The target is the thing that might have to get rebuilt. And after the target, there's a colon, and then there's a list of prerequisites. The list of prerequisites says all the stuff that the target depends on. So you can think of the top line of a rule as saying, whenever any one of these things changes, whenever it gets modified, you need to rebuild this target. After this line that has a target and a prerequisite, you can have a list of commands, a list of shell commands that show how to rebuild that, the target. So you can think of this sequence of commands as, let me re-say the whole rule. You can think of this rule as saying, you need to rebuild this target whenever any of these files gets modified, whenever any of them get updated, and here's how to do it. You run this sequence of commands. In this class, we normally try to avoid hard tabs. Our style guidelines say that in your source code, we're not going to include any hard tabs, but this is one place where we have to use them. In a makefile, all of these shell commands, all the instructions that show how to rebuild the target when a prerequisite changes, these have to start with hard tabs. So even though we avoid them kind of in every other part of the class, this is one place where we have to include them. So if we had to write a makefile to rebuild this simple project we've been looking at, what could it look like? Well, we just need a rule for each of the things that we might have to build. So this is a way of trying to capture the compile instructions to build a non-trivial project. Like we did a couple of slides ago, to rebuild our executable, we need to link together two object files, main.o and stuff.o. And this is the compiler instruction that will do that. So our first rule, the first rule I put in here is whenever either of these object files gets changed, you need to rebuild the executable, and here's the compiler rule to do that. You need to link together these two object files into an executable named main. Where do these two object files come from? We can have other rules for that. The main.o file depends on its own .c file. And if we look at the top of that, it also includes stuff.h. So if either of these change, we need to recompile to generate main.o. This is the same compiler instruction we ran a couple of slides ago to recompile main.c into an object file. Same thing for stuff.o. If either its .c file or its header file changes, we need to rerun the compiler to rebuild that. I can show this off. I've got a so here's the same source files we were just looking at. If you take a look, I've got the make file we were just looking at. This should be uploaded to Moodle today. So if you want to take a look at this make file and try it out yourself, you ought to be able to do that. I snuck in some comments to try to explain what's going on in this make file. here in the shell window, I'm going to, let's remove everything we've built already, just so that we can give the Makefile a chance to do what it does. So I'm going to remove main and main.o and stuff.o. And so here you can see we've got the Makefile and we've got our source file main.c and our two other source files, stuff.c and stuff.h. If we were, so I probably should have said this when I was talking about the Makefile, but the way you run make is you run a command called make, and if you don't tell it anything else, it will automatically look for a file called Makefile in the current directory, and it'll try to follow the instructions in that file for what it wants to build. In this case, make automatically prints out all the commands it's running. So it says, I want to rebuild main, but to do that, first I have to rebuild both of the object files that have to get linked together. So it runs the commands that rebuild those object files, and then it runs the command to link them together. And make is just, so I'm looking at the Makefile here. Make is just following the recipe that we put together here in our Makefile. So it said, I want to rebuild the executable that you asked me to build. But to do that, I need to first rebuild these two object files. And we gave it rules to rebuild each of those. Let me quickly show you some of the point of writing something like a Makefile is then if you have a big project and you don't want to type the commands to rebuild all the pieces of it, you can put all those in a Makefile, and then you can use make to get it to run those commands. And some of the point of doing that is make can be smart about what it rebuilds. Like, we just rebuilt our program using make. If we run it again, it says there's nothing to be rebuilt. Nothing, you haven't changed any of your source files, so I don't need to rebuild any pieces of it based on what you changed. We can lie to make, or we can make it look like we've changed one of our source files. Let me sneak in. And I'll sneak in a space here. So I'm changing this file, but not in a way that really matters. I snuck in an extra space in the declaration of the variable x. If I rerun make, you can see it, based on the rules that we defined, it rebuilt our project, but just the stuff that needed to be rebuilt. I changed stuff.c, so it recompiled the object file, stuff.o. And then since that object file changed, it also had to relink to build the executable. But it didn't do anything to recompile main.o, because I didn't change that file. It doesn't need to recompile it. It does need to relink to build the executable. So going back to my slides here, this is the same Makefile we were just looking at, just with the comments removed so that it fits on my slide. But each of these is a rule that says how to rebuild part of our project based on when things change. This is stuff I already said, but I'll try and go through it quickly. You can think of each rule in a Makefile as saying a target, something that you might have to rebuild, based on a list of prerequisites, things that the target depends on. So if any of these files change, you need to rebuild this, followed by a sequence of shell commands saying what commands to run to rebuild that thing. This is, this is a simplified makefile. You can, just like we saw when we were looking at that example of a makefile, you can include comments in your makefile to make it more meaningful to a reader, to help you remember what you were doing when you wrote that makefile. And this is what we just did when we were running that makefile. It tries to be smart about only rebuilding the stuff that needs to be rebuilt. There are some things that you can do to simplify a makefile, and I want to take a moment to show some of these. This is a makefile that does pretty much the same thing. It's just way shorter. And in this case, it's probably a bad example of a makefile, but in any makefile, you just have to have a sequence of rules that show what target needs to get rebuilt based on stuff that changes. So we could have written this makefile to say, well, you need to rebuild main whenever any of these source files change. And to do that, this is a command that you can run. And this makefile will work. It's just not as smart as the one that we were looking at previously, because it doesn't know how to rebuild your project selectively. In this one, if any of your source files change, it's going to recompile all of your source files and relink them all together into an executable. And that's kind of the idea that we started with. For a large project, you don't want to have to recompile everything whenever any one thing changes. So this makefile, this 2-line makefile will work. It's just not nearly as efficient as the one I've listed here. But it is awfully easy to write. And it would be nice if make could do a little bit of work for us, if we could write simpler makefiles, backing up a couple of slides, simpler ones in this, and we can. That's what I'm trying to sneak up on. It's just, this is not the right way to do it. Make has built-in rules that know how to rebuild stuff, that know how to rebuild objects when a source file changes, that know how to relink your project together. And if you ask it, if you run make like this, it will tell you all of its built-in rules. Last time I ran that, it printed out about 1,000 lines of output saying all of the built-in rules that make knows how to use. Based on those built-in rules, you can get make to rebuild stuff for you using its default, using its built-in rules. And using that, you can write a makefile that is as simple as the one I've listed down here at the bottom. Here, I just told make about the dependencies. So I said, you need to rebuild main whenever stuff.o changes. I didn't say main.o there because make is smart enough to guess that. If I've got an executable named main and I have a main.o in the same directory, make is smart enough to know that main.o depends, the executable main depends on that. Same thing with these next two rules. If I list main.o and I don't list a .c file, main.c, it's smart enough to know main.o probably depends on a source file with the same name. Same thing down here, I didn't list the .c file that stuff depends on, and it is smart enough to guess that. But it is not smart enough to know what compiler options I might want. Make knows that A .o file probably depends on a .c file that has the same prefix, but it isn't necessarily smart enough to know that I'm using the 99 standard of C. There is a way to specify that stuff. The default rules include use of variables that let you sneak in compiler options that you might need. And to use these, we just need to learn how make supports variables. In make, you can specify variables and assign them to values like I'm showing down here. So make lets you name variables any identifier name you want. And then if you use an equal sign, everything else on the line after the equals is whatever string that evaluates to gets assigned to the variable. You can use this to commonly to keep up with list of files in your make file. So it might be common to have a list of all the source files in your program, and to use a variable to keep up with that list. You could have variables that are assigned to the value of other variables, like I'm trying to show on this next line. So here, whatever's in the source files variable, along with whatever's in this object files variable, along with whatever's in this executable variable. All of those will get expanded by make and assigned to this variable here. And that's handy for defining a make file where you don't have to keep saying the same thing over and over again. You can have variables that keep up with lists of files. But the reason we got here is this is also handy because the default rules for compiling and linking use standard variables that make takes advantage of. The variable CC is the name of the default compiler that gets used. So if you didn't want to use GCC, or you wanted to specify the name of the compiler that gets executed, setting this variable to something would let you do that. This variable cflags lets you specify default compiler options. And this variable ld_libs lets you specify default libraries that you might link with. So if you needed the math library, you could set this ld_libs to -lm, and that would automatically link with the math library. So backing up a slide or two, this is a makefile that uses the default rules, but if we don't say anything else, it doesn't include any of the compiler options that we might want. This makefile uses the default rules, but using variables like we've been talking about lets us modify those default rules so that they include additional compiler options that we might want. I just said the variable CC lets you specify what compiler you want to run. So if we set that to GCC, when it runs the compiler for any of these rules, that's the compiler we're going to get. And cflags lets us specify compile time options. So if we set that to -wal -st, our standard options, -wal -std equals C99, then whenever it compiles our program, it's going to use those two options. I'm hesitating because I think I have an example of this. Yes, so this is a makefile. It compiles exactly the same thing we were just looking at. This is just one that uses the built-in rules for make. And here with some comments, you can see I'm setting these two variables to use the GCC compiler and to set up our standard compiler options. And then down at the bottom, I'm using default rules to build an executable based on these two object files. And then for each of the two object files, I'm using built-in rules to compile those. But since I told it what compiler flags to use up here, I don't have to specify the whole rule for that. I'm using the default rule with these extra compiler flags included. There's a lot more to make than what we're going to get to talk about in this class. We're learning just enough to build some simple makefiles. Later, for later projects, we'll start defining rules for getting make to rebuild a project from scratch. So we'll define rules that let us delete temporary files. If you've got multiple makefiles, like I just showed you in that example, I didn't properly explain it, but if you take a look, I've got a makefile called makefile, and I've got one called makefile2. If you just run plain old make, you're going to get this first makefile by default. But if you specify the -f flag, you can pick which makefile you want to use. Makefile, I mentioned that it comes with a bunch of rules that are built in. You can define reusable rules like that yourself. You can define other things like what to do if a rule fails. We won't use these last things this semester, but if you were building a big project with make, these would be features that you might want to take advantage of. A disadvantage of make is so an advantage of it is it lets you express the dependency structure within your project. But the instructions for how to rebuild anything are shell commands, which means that a makefile is only going to work on a machine that has a shell, that has something like, that's like a Unix machine, that has a built-in shell interpreter. Lots of systems have extended this idea of make, the idea of being able to automate the build of a non-trivial project. And they fixed some of the things that I'm talking about. I've listed here a number of alternatives to make. I think the idea of build automation shows up all over the place. It's just make was one of the first examples of a tool that did that. And even if you're using a integrated development environment like Eclipse, internally, it is using some build automation tools. It's just as you add source files to your project, it's keeping up with all those source files and keeping up with how to build your project and using a tool to rebuild your project. You just don't have to necessarily write the makefile yourself, but a lot of that stuff is still happening internally. If you're working in Java using Eclipse, I haven't checked lately, but I think it's still using Ant. And there are a number of newer build automation tools that are still getting used today. And that gets us caught up with where we were supposed to be at the end of class on Thursday of last week. I probably could have gone through that a little faster. Before we move on, are there any questions? All right, I'm hearing silence, so I hope that means there are no questions. Feel free to interrupt me partway through if you have questions. It is it is easier to deliver lectures with a little bit of interruption every so often. All right, so what we're supposed to cover for today, or what we were supposed to cover for Tuesday of this week, if classes hadn't been canceled that day. So we're supposed to start talking about arrays in C. There are a lot of ideas, there are a lot of topics that we'll need to cover to get through everything about arrays. Fortunately, most of you are coming from some background in Java, so the idea of an array is something you're familiar with. We just need to fill in a few missing details based on C. Just like in Java, when you're defining an array, there are a few. There are three things that you have to describe. An array, when you make an array, you have to say what type of thing is in the array. I'm hesitating, I apologize, I'm hesitating because I should say what an array is. An array is a big list of values, all of them the same type, just like it is in Java. So if you want to make an array, you have to say how many values are in the list. So that's the size of the array, the number of elements in the array. You have to say what type of value there are. That's the type of the element in the array. And you have to say how the array is going to get allocated. In C, this is, like I've been pointing to with my mouse, this is how you notate that. It's a little different from Java, because in Java, the square brackets saying that this thing is an array, they go here right after the type, at least they can. And in Java, declaring a variable that is an array type doesn't really allocate that array. It makes a reference, and you're expected to allocate it usually in a different expression. But in C, the type of the element goes first, and then the name of the array you're making, and then inside square brackets, the number of elements in the array. This is a little bit weird because it's kind of like the type for the array comes in two pieces. The stuff out front is the type of each element, and the stuff at the end is the size of the array. I'll mention that in some places, the size of the array has to be a constant expression. I can think of two cases where that's required. And the only one we've seen so far is for global variables. If you make an array that's a global variable, its size has to be a constant expression. If you make an array that is a local variable, as of C99, its size can be determined by a variable. So this is backing up, this is how you make an array. In Java, if you were declaring a variable that was an array type, then you would also have to allocate the variable, but not so in C. If you declare a variable like this, then you've already made an array. So if you said int a10, you've got a 10 element array of integers that's already been allocated for you. How do you use it? The notation is just like Java. At least you can use the same notation as Java. If you put the name of the array in front and then an index inside square brackets, that's how you access individual elements of the array. And just like Java, the indices range from 0 up to the size of the array -1. So backing up, if you made a 10 element array of ints like this, you could access A with 0 inside square brackets, all the way up to A with 9 inside square brackets to access all 10 of its elements. You can also do it this way I'm showing at the bottom. We'll talk a little bit later about why that works. Most people wouldn't access an array like that, but if you want, you can put the index outside the square brackets and the name of the array inside square brackets, and it works just fine. It works just like this notation up at the start. Some textbooks like to use that notation, but I would say most people use arrays like I'm showing up here. And like I said, we'll talk in a lecture or two about why this kind of goofy backward notation for accessing an array, why that works in the first place. This I kind of covered a couple of slides ago. In C, when you declare an array, like the code I've got on the left, that goes ahead and makes the array. You can allocate arrays as local variables. So they can be allocated on the stack just like any auto variable. You can allocate them as global variables, and their initialization behaves just like any other variable accessed in that region. So if you allocate an array on the stack and you don't initialize it, then it's going to start out with elements where you really don't know anything. You can't make any guarantees about what those elements start out as. If you allocate it globally, if you allocate it statically, then just like any other statically allocated variable, it's guaranteed to start out full of zeros. If we compare this to Java, this is what I said a couple of slides ago. When you declare an array variable, that doesn't automatically allocate it. You still have to make a call to the new operator to create that. And in Java, all arrays are allocated on in the same region of memory. You don't get to choose where arrays are allocated. If I had to compare it to C, I would say in Java, all arrays are allocated on the heap. We haven't learned how to do heap allocation yet in C, but that's a couple of days away. In C, we can allocate arrays just like, we can allocate them just like heap, just like we do in Java. We just have the choice of being able to allocate them just like any other stack variable, or statically, just like any global variable. Questions before I move on? I said this a slide or two ago. For arrays, if you don't initialize them, then their initialization behaves just like any other variable. So here, pretend I've got this little bit of code. Pretend this is inside a function. If I make this array A and I don't initialize it to anything, then I start looking at its values like I'm trying to do here. Then just like any stack variable, it's going to start out uninitialized. It'll start out containing whatever happened to be in the memory that that variable is using. If I statically allocated it, then even if, just like any statically allocated variable, if I statically allocated, if I declare it as global or a static local variable, then it's guaranteed to initialize to zeros if I don't initialize it. And this little fragment of code, when I ran this, when I first wrote this slide, this is what got printed out. And this is showing that this 20 element array of ints, if I don't put anything in it, it starts out containing whatever happened to be in that memory before I started to use it. What if you wanted to initialize a variable? So what if you wanted to initialize an array? If you'll let me back up a slide, you can do it one element at a time, like I'm trying to show here. You could, here I'm declaring an array A, and then I'm filling in its elements one at a time. But arrays also support an initialization syntax that can simplify this a lot. When you declare an array, you can go ahead and specify, just like a lot like any other variable, you can declare the array and then have an equal sign, and then inside curly brackets, you can list a series of values that should go into every array element. So in this initialization, 7 is going to go into element 0, 14 is going to go into element 1, 21 is going to go into element 2, and so on. This initialization syntax can let you specify all the values that go into an array. You can also do what's called partial initialization. Down here at the bottom, I'm showing making a 5-element array, but I don't give 5 initialization values. I only give 3 here. If you partially initialize an array, the compiler automatically writes code to put every value you specify into an array element. So starting from element 0, so 7 will go into element 0 here, 14 will go into element 1. The elements you leave out with partial initialization syntax, the compiler automatically assigns those to 0. So even though I didn't say anything past what I wanted element 2 to have, the compiler will write code to initialize all those elements to 0.
Excuse
yes, me. Thank you for the question.
So if you just wanted your array initialized to contain all zeros, you would just put down int a, however many indexes equals, and just 2 empty braces?
That's a good question. I looked, and that seems to work on GCC. I looked at the standard for that, and according to the standard, it looks like you have to have something inside the curly brackets. But the compiler we're using seems to be tolerant even if you don't.
Would it be better to just put 1 0 and let the rest just be?
I agree. So if you wanted to write code that you felt guaranteed would be portable, you could put a single 0 inside the curly brackets, and then that value would get set to 0, and everything else would get set to 0. I don't know if I've ever found a compiler that required you to put something inside the curly brackets, but looking at the standard, it seems like the stuff inside the curlies has to be non-empty.
Okay, thank you.
If it helps, for us, for this semester, we're going to follow what GCC does. So it's perfectly okay to have an initialization expression like this with nothing inside the curly brackets, even if maybe that is inconsistent with the standard. Any other questions before we move on? All right, so the point of this slide is You can initialize all the values in an array by listing them all out inside curly brackets. You can do partial initialization by listing just some values, and any of the remaining ones that you leave out will automatically get initialized to 0. If you have an initialization expression, you can use that to let the compiler determine the size of your array. Normally in C, when you declare an array, you have to pick the size for it. But in this case up here, if I'm giving 5 elements, the compiler is smart enough to say, you gave me 5 initialization values, you must want a 5-element array. So that you can use the initialization expression to pick the size of the array if you need to, if you want to. In C99, they came up with an alternative initialization syntax that lets you just initialize some values rather than having to do them in order. And down here at the bottom, this is what it looks like. If you want, you can specify the index inside, so inside the initialization expression, inside the curly brackets. You can specify the index inside square brackets, and then the value it gets after an equal sign. And this would let you, it would let you jump around if you wanted. You wouldn't have to initialize things in order. And you wouldn't even have to initialize everything. In this case, I'm initializing element 7 to 10. So that's where this 10 here at the end came from. It's silly to do it this way, but just to show how this syntax works, then I go back and say, oh, I want element 2 to get a 40. So that's where this 40 came from. And then I want element 5 to get a 35. So that's where this value came from. Just like any other partial initialization, the stuff that I leave out gets initialized to 0. If I don't specify the size of the array, like I did here, it will choose a size that is big enough to hold the largest index that I use. So since element 7 is the largest one that I specify, this array has 8 elements, 0 up to and including 7. You can, yes.
I'm sorry. Is this one of those times where the compiler will yell at you if you leave a variable as the index you're defining? Like instead of bracket 7 bracket equals 10, it was bracket I bracket equals 10. And
so I think you're talking about a constant expression there. I don't know if I've ever tried that, but I think the rules are going to be the same as they would be for any array initialization. So an array that's defined as a local variable, the thing inside the brackets could be a variable, but honestly, I'm not sure I've ever tried that. And then I was going to say, if it was a global variable, I think it's going to need to be a constant expression. I'll check that. Okay. If I had to guess, I would say for local variable, it can be something the compiler has to evaluate at runtime. For a global variable, I think it is going to have to be a constant expression.
Thank you.
Other questions? All right, so here I was introducing array initialization syntax and the new way that you get to do this in C99. You can even mix these if you want. I wouldn't, but partly because it's potentially confusing to people who might be looking at your code, but the standard still says what this means. If you mix the initialization syntax, so if you start listing a value, the compiler is going to assume, oh, that's the value that goes in the next index. So this 1 here is going to go into element 0, and then 10 is going to go into element 7, because that's where you said you wanted to go. This 90 is going to go into element 8, because that's the index after the 7. So wherever you specify an index, that's where that element's going to go. Wherever you don't, it's just going to fill in the subsequent element of the array. So for this initialization syntax, this is the array you're going to get. The size of the array is going to be determined by whatever the largest index you specified is. So since this 90 ended up going into element 8, that's the last index of the array. So in this case, we have an 9-element array with indices from 0 up to and including 8. Arrays in C do not do any bounds checking. Unlike Java, where every time you access an array, it automatically checks to make sure you're not indexing off the end of the array. But in C, you can imagine that C always favors performance over security. It gives us ways of writing code that can run really fast. It's just up to the programmer to worry about whether or not the thing they're doing is a good idea. So you can think of an array like the one I'm declaring up here. I'm making an array of 6 elements as being stored in 6 consecutive integer-sized locations in memory. And if you accidentally index off the end of the array, so this 6-element array would have element 0 up to and including element 5. If you try to access elements past that, the compiler doesn't write any code to keep you from doing that. So that would let you access memory past the end of the array. Even if you try to access elements before this, if you try to access an element -1 at index -1 or -2, then you will be accessing memory before the start of the array. We can show this. So I wrote a little sample program. It's a bad program because it accesses memory off the end of the array. But it does show the kind of thing that I'm talking about. So here, I wrote a function that makes an array with 3 elements. And right before the array, it makes a variable x that gets a value of 25. And right past the end of the array, it makes a variable y that I put 50 into. And if I just print out the elements of the array, and that's what I'm doing on this first printout, you get exactly what you would expect. The array has 10, 20, and 30 in it. So that's what I get when I print out these elements. But if I back up and start looking at elements before the start of the array, like if I print out A at index -1 or A at index -2, I start seeing other stuff that is stored in memory. And you can see down here, when I print this out, I get some random looking value here, but right before the start of the array, I get a value of 50. And this would depend on your compiler and the system you're running on, but on the system I ran this on, I bet I'm looking at that value of y, even though I declared it after the array. It looks like the compiler decided to store that right before the start of this array. And same down here, when I start looking at element 3, element 4, both of which are kind of off the far end of the array, I see a 25, which I bet is that variable x. As you index off the end of an array, like I said, the compiler doesn't automatically include code to catch when you make a mistake like that, whereas Java guarantees that if you index off the end of an array, you'll get an exception thrown right away. In C, indexing off the end of the array could potentially let you access other variables in your program, not in a good way. If you accidentally write off the end of this array, you could accidentally be changing these two variables. And that is one of the most common sources of errors in a program, in a C program. What I tried to show on that previous slide is if you're indexing off the end of an array, so if you've got an array that's got a particular number of elements and you index past that number of elements, you're really looking around at other parts of the memory where your program is stored. If your array is stack allocated, so if it's allocated like any other local variable, then indexing off the end of the array is letting you look at and potentially change other stack allocated variables. Like a claim we just saw, they're stored, they may be stored consecutively in memory, and accidentally writing past the end of an array might let you change one of those when you didn't mean to. Feel like I've already said this. Indexing past the end of an array, accidentally writing to memory that it is out of the bounds for an array that has an index that's too large. If you let me back up a couple of slides, here it's maybe kind of fun to see how these variables are stored in memory, how they're stored on the stack. But in practice, this is likely to be a bug in your program. And it's likely to be something that's going to crash your program if you start writing to memory past the end of an array. Hopefully, if you make a mistake like that, it's going to crash your program right away. Bugs that crash your program right away, those tend to be easier to diagnose. But a trickier kind of bug to detect and diagnose is one where your program makes some kind of mistake, it writes to some memory that it shouldn't have, and then instead of crashing right away, it keeps running, and then maybe the thing that it accidentally overwrote doesn't affect the program for several minutes. And those tend to be the tougher bugs to detect. And that's what I'm trying to say down here at the bottom of the slide. If you have an array out of bounds error, hopefully that's something that's easy to detect and it'll crash your program immediately. The trickier ones are the ones that overwrite something that your program doesn't get around to noticing until a little bit later. And then it's hard to go back and figure out what caused a program like that to crash. Here I'm trying to show that since C doesn't do anything to prevent you from accessing past the bounds of an array, any array is potentially a way of accessing any of the memory of your program. Let's pretend you have an array here in the middle of the memory of your program. If you index past the end of it, you could be accessing other parts of your code or other parts of your program off this end of your array. If you accidentally use a negative index, you could accidentally be accessing stuff earlier in the memory of your program. So even though the choice in designing C so that it doesn't do bound checking on arrays, even though that potentially makes our programs a lot faster. It also leaves open a lot of potential security holes. And one of the most common of these is something called buffer overflow. Since C doesn't automatically check to detect when you access past the end of an array, it's really easy to accidentally write code that indexes past the end of an array. That's what I'm showing down here. A buffer overflow is when you've got an array and either a user or another programmer is able to trick your program into writing past the end of that array. So here I'm in an array with space for 20 elements. I got a loop that keeps reading elements into that array. So I'm going to read as many integers as you want to enter. But I don't have anything to keep it from writing past the 19th element. So if you keep typing in integers, it's going to write past the end of the last part of this array. And when it does that, who knows what element of memory it's going to start writing into. We are sadly out of time. Let me take a look ahead. We'll pick up here on at our next class meeting. Like I started to say, buffer overflow is in a C program. It's one of the most common ways of exploiting a vulnerability in a program. And if you're programming in C or a language like that, then that's something that you need to be aware of as one of your responsibilities for making sure that you don't have any vulnerabilities like that. We'll, I think we've got, a series of 3 security hazards that we'll talk about, but we'll save those for next time. Thanks for your attention. If you have any questions, hang around. Otherwise, I'm going to say that's all of our lecture for today.
I do have a question, and it's about Project 2. When will we be receiving like the description for that? Because it's due Wednesday.
So I'm working on Project 2 right now. The deadline, sorry, let me stop recording. The deadline will be extended.
Okay.
Yeah, so I won't give you a project and then ask you to turn it in 6 days.
Okay,